Hello and welcome to week 11. So, if you wanted to start your week with some more germ-related music, this was a popular song, well, when I was really, 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 really young by Johnny Rivers. It's called The Rocking Pneumonia and the Boogie Woogie Flu. If you've ever heard it, you know it has a pretty catchy rhythm. There's the YouTube link if you want to listen to it. There you go. So this week it's the antimicrobials. You've already had a little introduction. We were talking about all the structures of bacteria and why some of those structures are great targets, right? So we're going to revisit that. So we're going to talk about antibiotics and a lot more. So here are the objectives for the week. And the only assignment other than the quiz is the outline. Of course, that is going to be done before Sunday. I know it's Easter, if you're celebrating Easter. And it's also April Fool's Day if you're celebrating April Fool's Day. So you might want to get that in early. I know one of you has it in early, but make sure it's in there. Okay. All right. So we're going to talk about microbes, their hosts, and chemotherapy. And I have a picture of a pharmaceutical store where, well, people sometimes flock to stores that are north of the United States or south of the United States because drugs are cheaper, and that includes antibiotics. And I know a family where certain members will travel to Mexico every year to get drugs that are inexpensive. And understandably, a lot of the medications that, especially the senior citizens, have to take are very expensive. And they have to sometimes make some very hard decisions, if not impossible decisions. But interestingly enough, so the people who travel to Mexico will buy also antibiotics, in case somebody in the family gets a little sniffle. So that way they can just dole it out. And usually they hand these out, especially around Christmas time. So you can pretty much self medicate. Now, if you're wondering if any member in that family is a registered nurse or a nurse in any way or a medical professional in any way, no, they have no science background or medical background. All right. So hopefully we'll talk about why that's probably not a good idea. I just wanted to also point out that the hero throughout this whole story, at the end of the story, and well, actually, the story is not going to be ending, but the hero, the heroes are the infection control nurses because we rely too much on drugs, chemicals to control microorganisms, and they will always mutate faster than we can get FDA approval for new drugs. So we're not going to win this war unless we get smart really fast. So what are we going to do when we have complete clinical failure of every antibiotic available? Well, okay, we're going to be in trouble, but the infection control nurses, the people who say wash your hands, they will be saving lives, and we will have to rely on them more and more as time goes on. So more about this in a little bit. Here are some terms. Oops, here are the terms, and you already had the objectives earlier. So, okay. Here are a couple of pictures of petri dishes, and you can see things are growing on these petri dishes. So here we have a plate originally that had a lot of Staph aureus. And in the middle, there's this fuzzy little mold growing, and it's kind of greenish in the middle and whitish on the outer surface. This is actually the common bread mold known as Penicillium notatum. This is Staphylococcus aureus. Now you'll notice that the Staphylococcus aureus colonies don't go anywhere near the fungal organism. There's cells here that make up the fungal organism that secrete a little chemical known as penicillin. And as it diffuses through this agar, it kills all the bacteria in its way. And it shows that, okay, the bacteria have to be this far out to be safe from this antibiotic. So it's fungal organism versus bacterial organism. This is the flip side to that. This is a bacterial organism known as Bacillus subtilis, and it's surrounded by a fuzzy, fuzzy mold. Okay, and you can tell there's a little dead zone there. Sorry, I shouldn't have the link showing. I have to remember how yeah. That always messes things up. But you can see there's this little zone here. These zones of killing is known as the zone of inhibition. So this is bacteria killing fungi. This is fungi killing bacteria. You should also know that bacteria will kill bacteria. Why? Well, because they have to, well, sometimes microorganisms don't like sharing their habitat. They don't like sharing their food and resources, just like you would see in something larger like a forest or a prairie or something like that. There's competition and they have to figure out a way to fight one another. So they eat the cells, the bacterial cells and the fungal cells will manufacture chemicals and release them into the environment to keep everybody back. Interestingly enough, this is how we get antibiotics. In fact, the group that we're going to talk about later on, called the cephalosporins, were very much discovered this way. People went out into the soil and they found, they tried to find fungal organisms and bacteria that would fight off bacteria. So we had antibacterial antibiotics, and that's how he did it. But the first person who discovered all of this is that man at the very top. His name is Alexander Fleming. He was a Scotsman working in England at St. Mary's, and he was kind of messy in the laboratory, and he was desperately trying to figure out a way to control Staphylococcus aureus, and he was growing up the bacteria in petri dishes. Sorry, so there's Alexander Fleming, and this was about 1928. So he went away on a fishing trip, and when he came back, he found that one of his bacterial cultures of Staphylococcus aureus had been contaminated with a mold. Luckily, he didn't just pitch the plate out, he observed and he discovered penicillin. Um, so this mold, Penicillium notatum, was producing, as I said, the antibiotic penicillin. Alexander Fleming knew, well, maybe not instantly, but almost instantly, that something really important was going on. And eventually he realized that, oh goodness, you know, he has found something that will kill microorganisms, that will kill germs. And this was our first true and fairly safe way of controlling microorganisms in patients. So this was our first really good chemotherapeutic agent. Okay, and again, you have this little zone here known as the zone of inhibition. So the mold is producing a chemical, it diffuses through this thick stuff called agar. It's a lot like gelatin, and whatever it was hitting on the way, it killed them. So it killed those bacteria. That's the zone of inhibition. Okay, so just to see if you're listening, why do organisms such as penicillium bread mold make antibiotics? A, they manufacture unique chemicals that attack other microbes. B, they win turf by chemical warfare. C, they don't like sharing nutrients with other organisms. Or D, all of the above. Yes, D, all of the above. And pharmaceutical companies used to, in the day, they would look for microorganisms releasing chemicals like this. Pharmaceutical companies really don't do research in antibiotics anymore, just so you know. If you're thinking, well, why not? That's crazy. Why wouldn't they? It's not as if the germs are going away. Well, the pharmaceutical companies have to make a profit. And like I mentioned earlier, they know the bacteria are going to mutate faster than they can get an antibiotic. Just so you know, it takes sometimes upwards to 10, 12 years just to try to get an antibiotic on the market. Okay. And it's going to cost well over $1 billion. So if something happens, the drug doesn't work well, the bacteria become resistant, all right, they're out a lot of money. Pharmaceutical companies, they are in it for, I mean, they're not a nonprofit organization. So antibiotics are not very fruitful. Drug companies will make antibiotics for the gram positives. They're a little easier. Um, a lot of the drugs are Me Too drugs. That means they'll take a drug that's already out there and just tweak it slightly and put a new brand name on it. They will do that because it's already gone through most of the FDA tests. There's many different trials, patient trials that it has to go through. But for the most part, it's way too expensive and the payoff isn't very good. And a patent is only going to last for about 7 years. So, yeah, they just don't want to get into that business. It's better for them to go into, high blood pressure medicine or cholesterol medicine, because by golly, they're going to have you for a lifetime, aren't they? Yep. So, wah, wah, sad. But let's move on. Here's a very, very happy picture. I was in London with a friend and her daughter. Her daughter was living in London at the time, and we took 3 buses to have a haggis sandwich. Yes, a haggis sandwich. It was amazing. She said, "Oh, do you want to see Alexander Fleming's laboratory? It's around the corner." I was so happy. I had no idea we were going to be so very close to it. But this is St. Mary's Hospital. His laboratory was right here, and the museum left it pretty much like he did, which he is kind of messy. But if you go through these doors here, okay, you will see this is where the museum is. And there we are. Yes, that's me. My hair is a little redder at that point. And also, I put on a couple pounds in the last 2 years. Doggone it. Anyway, let's talk about some terms. Chemotherapy is the treatment of disease with a chemical agent. We call the agent a chemotherapeutic agent. Okay. Antimicrobial drug, that's a generic term. It means that it's a drug that's going to kill microorganisms. Antibacterials, being very specific, it kills bacteria, meaning not viruses, not mold, not protozoans, bacteria. Antibiotics is used as a very generic term, but technically, and for my class, an antibiotic is a metabolic product of living cells that are detrimental or inhibitory to certain microbes. Come back? Yeah, all right. So listen, an antibiotic is something that's made naturally. So when it came to the bread mold penicillium, the bread mold, the mold that was growing is a real living creature. Its cells manufactured penicillin. Thus, penicillin is a true antibiotic. Okay? Now, there are synthetic antimicrobials out there, and we will talk about ciprofloxacin, levofloxacin, totally synthetic, made in the laboratory. They did some computer modeling. But really, most of the drugs out there are semi-synthetic. Now, what does that mean? That means that they found a natural product like penicillin, and penicillin G is the one that you get injected, like, gee, that one hurts. Penicillin V would be the one that you take orally. That's pretty much the natural structure. But the problem with those drugs is some of them are excreted way too quickly. Some of them are only going to kill a certain type of bacteria or just a few certain kinds, well, just a few kinds of bacteria. So, maybe we could tweak it. We can, on that R group, we can tweak it just a little bit to make it stay in the tissue a little longer. Maybe make it also maybe a little less toxic. Not talking about penicillin here, but we can tweak it, make it a little more what we call broader spectrum. Speaking of which, let's define the difference between narrow spectrum antibiotics and broad spectrum. And I'm reasonably sure, ladies, that you are perfectly aware of this, but I still want to go through this. So narrow spectrum antibiotics means Pretty much, these drugs are only going to cover just a few types of microorganisms. Sorry. So that would be, for example, penicillin is going to knock out, for the most part, gram positives like staph and even strep, a few gram negatives, but not many. Broad spectrum. Now, that doesn't mean it's going to kill everything. It just means that it's broader than narrow spectrum. So, broader spectrum means that it would probably work on a lot of gram positives and a lot of gram negatives. Okay. Here's just some pictures of some broad spectrum antimicrobials. This is tetracycline, this is chloramphenicol, and these are erythromycin. They all have the same action. They all are going to stop cell uh, protein synthesis. But when you look at these structures, sometimes you can tell how well they're going to get into tissue. How would you know that? Well, if there is a charge, then probably they're going to be pretty bulky. They're not going to be really good at getting in there and going after microorganisms, especially if the bacteria may be slipped inside one of your white blood cells or one of your endothelial cells lining your red blood cells, or lining your blood vessels. Sorry, for something to get into a host cell that's infected. So if you want to go in and get maybe Rocky Mountain spotted fever inside a blood vessel cell, then you need something that looks like this. It looks like a race car. It looks sleek. It's not really charged. It's really going to go in there and get it. This one I always think looks like the Starship Enterprise. So that one's going to go in very easily as well. I know I'm very nerdy. Erythromycin, not bad, but it's not great. I mean, it's not going to be really great at slipping through phospholipid membranes and getting into a host cell that's been infected by a bacterial cell. Okay. So again, if it wanted, you wouldn't send this one into if a blood vessel cell had Rocky Mountain spotted fever. You wouldn't use this one. You'd use maybe this one. Or if you had to, that one. Story behind that one. So, antibiotics. When Alexander Fleming, and by the way, he wasn't the one to really produce the usable kind of antibiotic that we think of today. There was actually a team of Australians who used some of Alexander Fleming's preliminary work, and they built on that, and they made the first antibiotics. And everybody thought, magic bullet. Oh my goodness, we never need an infectious disease department anymore. Literally, colleges and universities considered just removing infectious diseases from like medical curricula. Like, oh, we don't need to learn about germs. If you got a germ, you just take an antibiotic, huh? So the magic pill, or was it? So there is one thing I want to mention to you. Okay, we can absolutely kill every single pathogen out there. Yes, we can do that right now. But the idea is keeping the host alive, okay, while you're doing it. All right, we can kill the microorganisms. In fact, we had some very useful drugs in the past, and here's one. So this is an old antique bottle. And so here are some tablets. This is number 92, and this is from Park Davis and Company, still running strong. So this has iron and arsenic and strychnine. Um, Strychnine used for rat poison, rat poisoning, arsenic as well. But hey, there is iron, and if you're kind of appalled at this, they are chocolate covered. So you could use this to treat syphilis, and they did, or mercury. So yeah, that'll kill the syphilis bacteria, Treponema pallidum. But is the host going to live through it? There you go. Well, there's always a drawback. So keep in mind that all drugs have a potential toxicity problem. All drugs. Talk to somebody in pharmacy school. They're usually appalled A lot of them try to make a pledge that they will never take any drug ever, ever, ever. So there isn't a drug out there that you can say it has no side effects. Okay? But we try, if we do have a patient who has an infection, the idea is to poison the bacterial organism, poison the pathogen, and leave the host healthy, right? We don't want it poisoning the host. We want it poisoning the bacteria. So yeah, this was for syphilis. So this all has to do with selective toxicity. Um, so when we talk about these drugs, these poisons against bacteria and pathogens, the idea is to find something in the bacteria or the pathogen. It's not always bacteria, it could be fungal. It could be a virus or something like that. But we have to find something that the poison attacks in that pathogen, and we need to find something that that drug can't hurt us. Okay, that's selective toxicity. It means that the drug doesn't target similar structures here. Okay, so you have all these cells, and you take a drug or it's injected, and it's going to go throughout the whole body, and it's going to be passing cells like this. Um, Maybe it even has to enter one of our cells to get at an intracellular bacterium or virus. Okay, well, yeah, we don't want it targeting any of our eukaryotic structures, right? Right, that's selective toxicity. Oops. Okay. So, golly, what is the ideal antimicrobial drug? Well, if you could find the perfect antimicrobial drug, you would be one of the wealthiest people in the world and you would be one of the greatest heroes. But this is what you'd have to do. The drug would have to have selective toxicity, meaning it would have to find something in the microbe that does not exist in one of our cells. The closest we can come to that is penicillin. Penicillin targets a very unique enzyme known as PBP. Only bacteria have that enzyme PBP, right? So that would be nice. Narrow spectrum. Why narrow spectrum? Because we do not want to eliminate the normal microbiota. If we went broad spectrum, like, oh, let's just give them a broad spectrum, see what happens. Well, what happens these days is C. diff. Okay. So, no, let's try to get something that just targets the pathogen and leaves the other good guys alone. A lot of drugs you take will wipe out your normal microbiota. And if you've ever been on an antibiotic and you had diarrhea, not necessarily C. diff, but you had diarrhea, or you had constipation, well, you're messing with the balance of your normal microbiota and you will feel it. Okay. So there we are. You have to have a drug that the bacteria can't resist. So the bacteria can't accidentally, and they do accidentally develop little mutations in their genes. Okay, and these little mutations in their genes give them the ability to resist the antibiotic drugs. Okay, so you have to develop some kind of drug where the bacteria just, no matter how many mutations they get, they can't mutate their way around the drug. Okay, we thought we had this with vancomycin and the gram positives. Oops, it took about 40 years, multiple mutations, actually combinations of mutations. I believe about 7, if I'm not mistaken. But they were able to do it. No undesirable side effects. Now, this is an issue with penicillin. As much as I love penicillin, if I take it, I'm going to get a rash, and oh, it's going to look something like this. Oh, actually, it would look much worse, actually. I would probably have anaphylaxis and die. So it would be good not to have any toxicity. We'd rather not lose a kidney while taking chemotherapeutic agents, right? I'm treating myself for a urinary tract infection, but in the process, I lost my kidneys. That's not good. And again, you don't want to lose your normal microbiota. So no undesirable side effects. All right. So what are all the targets of these drugs? Well, I'll tell you what, we're going to start off by talking about bacteria. I am going to blend in antimicrobials that will also go after fungal organisms, and we are going to talk about antivirals to boot. Okay, so when talking about the antibacterial drugs, those drugs that will only go after bacteria, okay, I'm going to start off and put them in order, grouping them together. We're going to first start about all those drugs that attack cell wall synthesis. And of course, you learned about penicillin. So, yeah, that will include penicillin. Then we're going to go after the drugs that go after uh, protein synthesis and then nucleic acid synthesis. And then we'll talk about sulfa drugs that go after folate or folic acid synthesis and a few others. Okay. All right. So the first group, what are we going to talk about first? Sorry, this all came up at once. We're going to talk about cell wall synthesis inhibitors. So if you know that that drug came up at the beginning of this lecture, you can pretty much guess, oh, that must have been a cell wall synthesis inhibitor because that's what she talked about first. Okay? Now, there are several classes of cell wall synthesis inhibitors. They're all a little different. I'm going to spend the most time on the cell wall synthesis, the cell wall synthesis inhibiting group known as the beta-lactam group. Chances are, ladies, you've heard a physician say, well, we're going to give them a beta-lactam or we're going to give them a different beta-lactam. Oh yes, that they were on a beta-lactam before, but we're going to switch to something else. What are the physicians talking about? Well, maybe you already know this, but beta-lactam drugs have a very unique little structure known as a beta-lactam ring. It's here in red. So this little ring is the one that messes with PBP enzymes. So this is the beta-lactam ring. So all these drugs are known as beta-lactam drugs, and they include the following: penicillins. You knew that. Penicillins, you'll know this penicillins because they end in cillin, like penicillin G and ampicillin and amoxicillin. Now, another beta-lactam group very closely related to penicillin is the cephalosporins. And you'll know a cephalosporin because they sound like ceph. Now, Ceph can be either CEPH and CEF. Yes, there's a difference, but you don't need to know the difference. Only pharmacists really know. So, or someone who teaches micro, but yeah, just Ceph. So they are related to penicillins. They're all in the same family of beta-lactam drugs. And then the last group, known as the carbapenems. You will know a carbapenem by their name because it sounds like M&M and M&M, like Dory Penem, imipenem. Okay, so these are all beta-lactam drugs. So they're very good at selective toxicity. Okay, they're very good. So here's a picture of our bacterial cell. Sorry, I tried to remove some of the background and it looks like some holes were made in here. But what I wanted to point out was, okay, so in the cell structure, of course, you have a cell wall. Remember, the cell wall is there for strength. Without a cell wall, the bacterial cell could explode due to osmotic lysis. Cell walls are not membranes. They are not membranes. Membranes are semi-permeable structures that regulate movement of chemicals. No, no, no. This is for strength. And cell walls are made up of peptidoglycan, right? In bacterial cells, right? So here we have the bars, the NAG and NAM and NAG and NAM. That's the carb part of peptidoglycan. And then you have peptide, uh, well, the protein chains, the peptide chains here. And they sort of hang down and they need to be assembled by this little guy. And this is the PBP enzyme, right? So the PBP enzyme helps to link together the cell wall. Now, what would a beta-lactam drug do? Well, it blocks The PBP enzyme, right? The cell becomes unstable and can explode. That's what I call a good antibiotic. It kills the bacteria. We call that bactericidal action. Okay. So, just a little bit of detail in case you forgot. Or in case you need a little bit more here, a little more information. So, beta-lactam drugs have the beta-lactam structure, and their job is to go after the PBP enzymes. Those are the targets. Remember, I said you could pretend PBP stands for peptidoglycan building protein. So here's the PBP enzyme, and it's got the peptide chains and its little active site, and there you go. And it kind of links all these little cell wall chains together, which is really nice, right? So peptide chains now if there's penicillin, sorry, if there is penicillin and this yellow structure with a little red dot, that's the beta-lactam chain. So P for penicillin. This works as a competitive inhibitor. It gets into the active site of the PBP enzyme, blocking it. So what's the consequence? Well, then the peptide chains, they don't get linked. Okay. That means the bacterial cells, they're going to go on trying to divide and grow, but they're not going to have any rigid cell wall protection. Because of that, the cell will explode, or what we call lyse. Okay, this is bacterial lysis. Again, it's bactericidal, but just as a side note, it's only going to work for actively growing cells. Let's say the bacterial cell already has an intact cell wall and it's not growing or reproducing anytime soon. Well, then this drug is not going to be very useful. Okay. Also, you should know the beta-lactam drugs are pretty big and bulky. Yeah, they're very good at their job. But if you have an intracellular bacterial organism like Rickettsia rickettsii that causes Rocky Mountain spotted fever, if you remember, it gets into the endothelial cells, the lining of your blood vessels. Okay, this drug isn't going to work for this. You're just not going to be able to do this. Not for intracellular bacteria. But pound for pound, your beta-lactam drugs are going to be the best drugs to use for selective toxicity because they're going to knock out PBP enzymes, and these are nothing like anything we have. Okay? We don't have cell walls, and if we did, they wouldn't be made of peptidoglycan built by PBP enzymes. All right. All right, so I'm going to talk about a lot of different drugs and drug classes. Now, most of these drugs you've heard of before, I would hope. Also know that drugs usually have three different names. They have the chemist name. So Mr. Seberg would probably call it that name, but nobody in the healthcare professions do. We just don't. And then there's a generic term like ampicillin. Okay, but then there's also a company name, a brand name. Sometimes that would have the generic name in it. So you have to look at the label. All right. And it's the generic names that I'm going to use because those are the most easy to identify. Okay. Some of the drugs I'm going to say this is just FYI for your information only. Why do I do that? Because you're going to probably see these. So you need to understand that, that these drugs belong to a certain category, and you can always refer back to them if you're interested. So it's just to give you a little extra education if you're in the mood, okay? All right, and hopefully you are. So let's talk about the beta-lactam group and who's in there. So the first of the beta-lactam group again are the penicillins, and they're penicillins because they sound like psyllin. They are narrow spectrum, right? So they're most useful against gram-positive bacteria like Staphylococcus aureus. Okay. They will take out a few gram negatives, and they have been known to be used against some gram negatives, such as Neisseria. They used to be even used for Neisseria gonorrhea, but no more. Um, Penicillin G, this one's in red, so you need to know that. Originally, this one's from mold. Penicillin G is the one that is given in a shot. Okay. Now, like I said, penicillin G is narrow, but well, when they developed penicillin G, so that was the first one, and they said, well, this is really nice, but yeah, because it only attacks gram positives, is there a way that we could develop a broader spectrum penicillin or even an extended spectrum penicillin? And they did. Okay, and I have a video that'll show you a little animation. So they went from narrow spectrum to broad and extended spectrum penicillins. They were developed to kill, as you can imagine, more types of bacteria, and this would include ampicillin, which this you get, it's an injectable kind of penicillin, but it is broad spectrum. It's quite nice. This is semi-synthetic. Again, they had the original penicillin G. They tweaked it to make it more broad spectrum, and ampicillin commonly used in hospitals because it is nicely broad. There was also methicillin that was produced. Now, methicillin not only was produced to be a little broader, but it also was used for to treat bacteria that were becoming resistant to the penicillins. So the bacteria were mutating, and if you remember, mutations are accidental, they are random. They some mutations are harmful to a cell, like a bacterial cell. Some will make no impact at all, but some of those mutations were beneficial. So we developed methicillin, and again, this is a semi-synthetic, but the bacteria very quickly developed resistance against this. So even though we developed this to treat bacteria that were resistant to the penicillins, or I should say to penicillin G, the narrow spectrum, the bacteria very quickly developed resistance against methicillin, very quickly. So methicillin did not stay on the market very long. Um, by the way the bacteria developed resistance against this was very unique. The bacteria mutated their PBP gene. So the PBP enzyme changed and methicillin didn't hurt it. But this gave us a new term, methicillin-resistant Staphylococcus aureus. Now, I remember when my brother was in the hospital and he was colonized with with MRSA before they called it MRSA. And I remember, the nurse explaining methicillin-resistant Staph aureus incorrectly. So I thought, oh my goodness, I didn't really correct her because it wasn't anything that would make any big difference, but it would only serve to embarrass her. But I thought my nursing students will never, ever, ever say something so silly. So Staphylococcus aureus is Staphylococcus aureus. Okay. They divide, they mutate, and one type of Staphylococcus aureus had a little mutation, little accident that allowed it to make a different PBP enzyme, so it was resistant to methicillin. And then it got that group, that strain of Staphylococcus aureus is called MRSA, but it's still just Staph aureus. And then what you would do is give then the patient something else, not methicillin. Um, so we'll talk about that in just a little bit, what you could move on to. The next type of drug is piperacillin. You don't need to know that. It's used only in hospitals. Why? Because we don't want it out in the general public. Why? Because the bacteria, if the more we expose the bacteria to the drugs, the more opportunities they have um, to kind of work around it and develop those mutations. And the drugs will select for the bacteria with the mutations. So we keep them to ourselves. The biggest problem with penicillins is, well, yeah, you can produce an allergic reaction. So that's not good. And that's my problem. I can't have penicillins. Just like my father, just like my brother, we can't prove that there's a genetic link, but a lot of allergies we know and asthma seem to have some genetic components. So there you go. The other problem is that unfortunately, the gram-positive bacteria have randomly gotten these mutations and they've developed resistance genes and they are resistant to a lot of these drugs. Okay. Now, if you're wondering about MRSA, why do we call all resistant Staph aureus now MRSA, which we do? Because we're not using methicillin, but maybe you've noticed on the floor a lot of your patients have MRSA. And you're thinking, but Miss Eden said we don't use this. We haven't used this in a long time. Yes, it's a name that's stuck, MRSA. We just use it for all, multi-resistant Staph aureus. So maybe that's what we should call it instead. But originally it was methicillin-resistant Staph aureus. Now we just use MRSA as an alert. Okay, this is Staph aureus that is resistant to a lot of different kinds of actually penicillins. Okay. So here is the video that I promised that I said would come up. So here we have bacteria undergoing binary fission. The cell walls are keeping their shape, but over here the bacteria have penicillin. It'll rewind in just a minute, but you can see they're popping. So, right? So they're trying to grow and make more cell walls, but they're unstable. Water rushes into the cell and they explode. This is what happens when PBP enzymes cannot make a strong cell wall anymore. So yeah, this is pretty bactericidal, isn't it? It's going to kill those bacteria. Yeah, definitely. Just one thing also, there are different ways for bacteria to become resistant to penicillins. And I talked about the methicillin resistant Staph aureus form, and that was to change the PBP enzymes. But one of the things the bacteria were also able to do, they were able to produce little enzymes that would go out, and these are little exoenzymes, and the bacteria would release these into the environment. And these little enzymes, called penicillinases, would munch up penicillin. So it would inactivate the penicillin before it attacked the bacteria. Okay, more about that in just a little bit. Okay, so the next group are the cephalosporins. Again, still we're talking about the beta-lactam group, and they all are cell wall synthesis inhibitors, right? So what do the beta-lactam drugs attack? PBP enzymes, right? What do PBP enzymes do? They build cell walls, exactly. So, all right. So if the bacteria are not responding to the penicillins, maybe they're resistant to the penicillins you've been giving them, or maybe the penicillins weren't really as broad as you would like. Well, you might move to this other beta-lactam drug group. And these, again, are the cephalosporins identified by the Ceph. They sound like Ceph. Little FYI, these come from fungi and also some bacteria. So the cephalosporins, if you remember, I mentioned it earlier, pharmaceutical companies were combing the soil looking for fungi and bacteria that would make these chemicals. And it turns out that, yes, they had a certain chemical structure that put them all into the cephalosporin category, and they all had beta-lactam rings. These are pretty broad spectrum. Again, they worked really well until the bacteria were able to get a hold of a resistant genes or a hold of resistance genes. And so that made them resistant to the cephalosporins. Bummer. Pharmaceutical companies kept trying to make more and more generations. They tweaked them, the drugs, so that the bacteria couldn't destroy the drugs. And it's still a game in progress, but the drug companies put these into generations. Supposedly the first generation or the second generation is better at attacking bacteria that are resistant to the first generation. That isn't always true. It's kind of a It's kind of a drug company fallacy, actually. So the first generation include drugs such as cefazolin. You do not need to know this, but this is the first generation. The second generation has something called cefuroxime, but you can identify them, right? Because they sound like ceph. Okay, now the third generation, I do have an example for you to know. The third generation has drugs like cephalexin, known as K-Flex. Okay, so that would be the company name. Cephalexin is the generic term. Ceftriaxone, Rocephin, ceftazidime. So ceph. Okay, and so again, the bacteria started to develop resistance against these. Ceftazidime isn't too bad. And as far as the bacteria, took them a while to develop resistance against this one. Cefepime, this is what we really hold on to, especially if we have a gram-negative bacterium. We don't let the cefepime out of the hospitals. If the patient comes in with a gram-negative infection, of course, gram-negatives are harder to treat. Then, if that is the case, then we give them cefepime. FYI. Biggest problem with cephalosporins. Okay, here's the one interesting thing. If you are allergic to penicillins and you go to the pharmacist and you say, and you have a prescription for a cephalosporin, the bells will go off, the red flags will start flagging, and yeah, the pharmacist will say, one moment, please. The reason for this is if you are allergic to penicillins, there's a possibility that you're also allergic to cephalosporins. So for me, this could be life-threatening. And for some of your patients, it could as well. And well, it depends on which form of cephalosporin. There's lots of them. So here's what Dr. Ken Thompson from Creighton always said. Um, and I would honestly not do this. I did take a cephalosporin once, and I shouldn't have. I thought I was just so clever that they couldn't get to me, and I was okay, but still. Some pharmacists may recommend, okay, they may recommend that you get a tablet of the smallest dose of cephalosporin, and then you cut the tablet in half, and then half again, and with the EpiPen ready, and probably a trach tube, maybe give your patient a fourth of that tablet, the lowest dose possible. Usually, the worst allergic reactions that you're going to get, the life-threatening allergic reactions, will occur within the first 30 minutes after the dose. Um, but frankly, that's pretty scary. So maybe go on to another type of drug, another class, if there is one available, actually. Um, so there's another problem as well. The bacteria started develop, they randomly got these mutations, and in an environment of antibiotics, well, the antibiotics would select for the strongest. The antibiotics selected for the antibiotic resistant strains. So, yeah, so the bacteria were developing resistance against the cephalosporins. Now, here's the really bad news. For gram-negative bacteria, remember they're toughest to kill. If we cannot use any of the broad spectrum penicillins or the cephalosporins, we really only have one class of beta-lactam drugs to use. And we like beta-lactam drugs. Why? Because they have good selective toxicity. Okay? So the last drug is this one. These are the carbapenems. And you can always tell it's a carbapenem because they sound like M&M and M&Ms. I know this picture is probably grabbing your attention. This is what happens if you get a skin infection by a gram-negative bacterium known as Pseudomonas aeruginosa. If you go into a hot tub that didn't get cleaned out well with Clorox, you might come out of the hot tub looking like this. And believe me, this isn't the worst thing that Pseudomonas aeruginosa can do. And Pseudomonas aeruginosa is everywhere. It is in the pipes. You turn on the faucet, Pseudomonas is there, but it is very opportunistic. So if you heat up your skin or have a burn wound or a surgical wound, they will get in there. So if nothing else is working, like the cephalosporins didn't work, we turn to our carbapenems, and doggone it, they better work. And like everything else, these are beta-lactams, of course. Just so you know, they are a natural product of a bacterium known as Streptomyces cadia. You don't need to know that, but it does have a beta-lactam ring. It's got it. And this is just where it came from, if you want to see the pretty pictures of streptomyces. These are very nicely broad spectrum. These are great against something called Enterococcus fecalis and its cousin Enterococcus faecium. Okay, if you're thinking, I've never heard of these bacteria. All right, when we talk about vancomycin, there's VRE. Okay, so that's vancomycin-resistant Enterococcus, same organism. So this is something that we like to use against Enterococcus when we're not using vanc. Okay, and we also use it when Pseudomonas is not responding to the other drugs. Like this patient has Pseudomonas aeruginosa. We gave them penicillin or a cephalosporin. It didn't work, so we use a carbapenem. Like with all the beta-lactam drugs, they inhibit cell wall synthesis, and this is the last good option to treat gram-negative infections. Okay? So when gram-negatives can't be treated effectively with this drug, we consider this really bad. Why? Okay, so doesn't work. We gave them cephalosporins, we gave them carbapenems. What do we do next? Well, there is a group of drugs that we actually put on a shelf years ago because they were so toxic. They went after cell membranes. And those drugs, a lot of those are very, very, very toxic. And patients who were taking those were going on dialysis and needed transplants. So we'd rather not use those drugs, as you can imagine. But if the patient is going to die because of Pseudomonas, this is what this is what we're facing. Just a little side note, my brother, who is a quadriplegic, he died because of Pseudomonas in his lungs, as well as, by the way, C. diff. And no, he did not get that. He got that when he was in the hospital for a different condition. So that was called, so they were both nosocomial. He got them while in the hospital and he died from them. So serious. And there was nothing to treat it. So this is what you face. So, yeah, bacteria. There are a lot of bacteria out there that have multiple genes, not just one gene to change a PBP enzyme, but maybe, yeah, a gene to change a PBP enzyme and another gene too to knock out penicillin and another one to knock out cephalosporins and another gene to knock out carbapenems. And then what do you do? Yeah. So like I said, you're kind of in trouble. You have to move to some other kinds of drugs. Now, with gram positives, we do have other drugs out there. We have still vancomycin, okay? And if that doesn't work, some others. Gram negatives, we don't have a lot of options, okay? So again, MRSA, yes, it can be serious. Yes, it can kill your patient. But gram positives, we do have other drugs, other things that are available. But whenever you see something like carbapenemase or carbapenem resistance, be afraid. So in the LA Times some years back, they were talking about KPC bacteria. KPC stands for Klebsiella pneumonia, carbapenemase producer. I know that is a very big mouthful. Let's break it down. Klebsiella pneumonia is a very, very common bacterium Yes, it can cause pneumonia, but it can also get into the GI tract. It can cause septicemia. It is a very versatile gram-negative bacterium. Well, so this bacterium got a hold of a lot of resistance genes, including a gene that made a little enzyme that would chew up carbapenem drugs. So that enzyme is a carbapenemase. So these are carbapenem resistant bacteria. These aren't the only bacteria that have carbapenemase genes. There are a lot out there, and it is scary. And it is what keeps most medical microbiologists up at night. And I do worry about it, and I will talk about why. You're going to be facing a lot of problems in your future. Here's one thing that happens as well. This is really where you're going to see some problems. A lot of your patients may have done a little medical tourism. What is that exactly? They'll go to other countries to get surgical care, to get a cheaper medical procedure. Sometimes it is plastic surgery, sometimes it's a little more serious. Um, Patients have been known to come back carrying these particular very microorganisms, gram negatives, I should say, these gram negative bacteria, and they get into the hospital, and the hospital staff, they can't find anything to treat the patient. It's called clinical failure, complete clinical failure. It's not just that patient, though. Many cases have occurred, especially in New York City hospitals, where the patient who is carrying these resistant bacteria, well, let's just say that they were put into ICU and the staff carried the resistant bacteria to the other people in ICU. And a lot of people didn't come out of that. Okay. So it's very, very scary. We see a lot of problems when patients are coming from India and Africa because there's not a lot of drug regulation there. Okay, it's a big problem everywhere. These bacteria, especially if you don't, sometimes if you don't have good sanitation, the bacteria are going to be everywhere. They're going to be in the soil, in the water, in the food, on the tables, on the counters, everywhere. And this is just bacteria in general. And if you have a lot of antibiotics, it will select for antibiotic variants. By the way, animals we know are also carrying these bacteria. So if you get pooped on by from a bird flying overhead, chances are there's a good chance that bird is carrying antibiotic resistant bacteria. So if you see anything like this, think really bad. This is bad. Okay. All right. Let's go back and let's finish the cell wall synthesis inhibitors. I only have a couple more. This next one is also a cell wall synthesis inhibitor, but it is not in the beta-lactam class. So the chemical is known, or the drug is known as bacitracin, not a beta-lactam. These are usually found in ointments. It does stop cell wall synthesis, but what it does is that it blocks another step in the cell wall production. So bacterial cell walls take place in many, many, many steps. We've only talked about one step, and that's the one the PBP enzyme is involved in. But there's another step where part of the peptidoglycan has to be moved from the inside of the cell to the outside of the cell. There's a little lipid carrier molecule that does this. Bacitracin blocks that. The one thing to know, though, is that bacitracin is only used topically because it's very toxic, way too toxic for oral use. And it is over the counter. So you probably do know that. All right, now for the big V, the big VANK. This one does stop cell wall synthesis, and it blocks a process. Actually, it the step of cell wall production is that last step. So vancomycin is kind of inhibiting the same types of step that penicillin inhibits, but it's different, okay? So it inhibits the same step, but in a different way. So vancomycin, the big vanc, not a beta-lactam drug. It will not lodge itself in the PBP enzyme. It does something else. So it is huge. Look at this monstrosity over here, this chemical structure. So do you think this is going to get deep into tissue? No. Intracellularly? No. Uh-uh. So the one thing about Vanc, if you take it orally, it will kill anything in your intestines that you want it to kill, and it won't escape your intestines because it's not going to go through the tissue in between the cells at all. But to give it to a patient, if the infection is systemic, like it's in the bloodstream, then you have to give this as an injection. It's an injectable, okay? Because it's too big otherwise. You can't take it orally and expect it to somehow get out of your intestines and travel to your lungs or wherever where your staph infection is. Yeah, too big. Very narrow spectrum. It's only going to work on gram positives. We always considered that, oh, and the target of this is still the peptide links. So here we have the chains, and you're like, okay. Vancomycin would be these big blue things. So that's why I drew this thing down here. This is supposed to be the big blue. So what this thing does, vancomycin grabs onto the end of the chains. So the PBP enzyme it can bump into it, but yeah, the PBP enzyme, basically the chains won't fit down into the active site of the PBP enzyme. Okay, so it attaches to the chains, blocks the PBP enzyme. So it isn't really considered a competitive inhibitor of the PBP enzyme like beta-lactam drugs, and it doesn't even have a beta-lactam ring. But even so, the consequences to the bacterial cell are the same. That means the cell wall is still weak and the cell can explode. Oh, sorry, due to osmotic lysis. Okay, uh, sound effects. The problem with vancomycin is that it is very toxic. It is, and it's also very expensive. Vancomycin we use as our last defense against Staphylococcus aureus. We would never use Vanc against Staph aureus unless it was resistant. Okay. So if Staph aureus was resistant to all the penicillins, to the cephalosporins, then we probably would use Vanc. Okay, so it's good against MRSA. Like I said, we thought the bacteria would never develop resistance against this because it's pretty effective at kind of gumming up the works and blocking the peptide chains here that are hanging down. There were some Enterococcus fecalis and Enterococcus faecium bacteria that live in the gut of humans, and they normally don't cause a big problem unless you have some abdominal surgery or wound. But still, they're in the gut, and when exposed to a lot of vancomycin drugs, let's just say they're very good at accumulating mutations, and they did. They were the first to become fully resistant to vancomycin. We call these vancomycin resistant enterococci or enterococcus, VRE. Let me tell you when these became resistant to Vanc, I will tell you that the infectious disease doctors were flipping out. Every meeting I went to, and I went to Creighton symposiums for years, and that has always been the main topic. They knew that this was bad. There were some other drugs that would come on the market, like Sinercid and linezolid, and some other things that will work against resistant Staph aureus and resistant gram positives. But understand, there's always some mutant out there that does not respond. Okay? So really, so we cannot be complacent and think that we can treat every staph infection because we can't. Okay. We can come close if we catch it early enough. But yeah. And here's something you should know about Enterococcus faecalis, or Enterococcus in general, is that they are really closely related to Staph aureus. And well, when you have close cousins, they do share genetic information. So VRE gave the gene to Staphylococcus aureus. And at first, it became a vancomycin intermediate Staphylococcus aureus strain that was dubbed Visa. Now, the Visa credit card people weren't happy about that, and they tried, and the medical people said, okay, we'll call it something else. No, we just call it Visa. But yeah. And then the Staphylococcus aureus had an opportunity and lots of opportunities for growth and replication and mutations. And one eventually did come up with vancomycin resistance, and that is Verza, vancomycin resistant Staph aureus. Okay, so that's when we had to move to some of the other drugs. So, and that's just to show you this is how this vancomycin kind of wraps itself around the peptide chains. I know, molecularly everything is a little strange. One thing I did want to mention also is that vancomycin is also known to cause something called red man syndrome. If the dosing is too rapid, you might get a shockingly red reaction, like red skin. Your patient will look, actually, if you know the Husker red. So, or well, this red, and it's due to rapid infusion of the first dose of vancomycin. Side note here, other antibiotics can also cause red man syndrome, but this is one of the consequences of vancomycin use, okay? Okay, so now we're going to talk about the protein synthesis inhibitors. If you're looking at this picture, okay, yes, this is the ribosome. But before we do this, okay, so we just left the cell wall synthesis inhibitors that included the beta-lactam drugs. They all have a beta-lactam ring, and they all block PBP enzymes, right? All right. So what are the beta-lactam drugs? We have, of course, the penicillins, psyllins. We have the cephalosporins, the cephs. We have the carbapenems and M&Ms. What's the advantage? Why do I love the beta-lactam drugs so much? Because they have good selective toxicity. Okay, they kill the bacteria a little better than they would hurt us. Okay, so we like that. But don't forget also that if our gram-negative bacteria are resistant against all the beta-lactam drugs, this is bad. This is really, really bad. Now, gram-positives, if they're resistant to all the beta-lactam drugs, we still have VANC. If VANC doesn't work, there are a few others, but still, this isn't very good. And sometimes, though, we can move to protein synthesis inhibitors. Okay, so why? Well, first of all, when we talk about protein synthesis inhibitors, these are, of course, medications that inhibit protein synthesis, transcription, or most of the time translation. They're going to either block the 50S portion of the ribosome. Remember, ribosomes make proteins. You're going to block protein synthesis, block the ribosomes. Okay, that's one good way. So the drug can block the 50S portion or the 30S portion of the ribosome or block transfer RNA. One of the things about protein synthesis inhibitors is that they are usually bacteriostatic, not bactericidal. What do I mean by that? So they're not going to kill most of them. There are a few that will kill the bacteria, and I'll talk about those. Most are bacteriostatic. Well, then what's the point of having a drug that won't even kill the bacteria? Understand that sometimes you don't need to totally destroy the bacterial cell. If the patient has a reasonably good working immune system, you stop the bacteria from making proteins. That means they're not going to be able to divide by binary fission. And then a white blood cell will come along and munch and kill it. So the immune system will clean house. You just have to stop them from replicating. The one thing about bacteriostatic drugs, though, is you have to keep the concentration up there. Why? Well, okay, let's say I block a ribosome with my protein synthesis drug. So I take a drug like Z-Pak, and it blocks the ribosome. Okay, the bacterial cell isn't dead, but if the bacterial cell decides, well, fine, I'll make more ribosomes, which they can do. If they go in and make more ribosomes, well, they'll just start replicating again. So, so again, you have to keep the drug up there so that every time they make a new ribosome, there's a new drug to block the ribosome. Okay. So, why is this going to work? Well, because all cells make proteins and bacterial cells also make proteins, and we can block those. Why is this a unique target? Well, remember, bacteria are prokaryotes, and prokaryotes have 70S ribosomes. So, this is pretty unique to bacteria and prokaryotic cells. Selective toxicity is, well, not too bad. Okay. So yeah, eukaryotes have 80S ribosomes. So they're kind of close. There is one problem that can happen though. Every one of your cells, right? They're eukaryotic. They have mitochondria. The powerhouse of the cell. The things that make ATP. The energy for the cell. Anything happens to the mitochondria and the whole cell dies. Mitochondria are very prokaryotic. They have a double membrane. They have their own single circular chromosome, which, by the way, is very prokaryotic. And they have 70S ribosomes. So if the drug is so good at getting into membranes, there's the risk of it getting into through the mitochondrial membrane and getting to the 70S ribosome. This is going to produce some major toxicity problems, okay? So those drugs that are really race car-like, okay, they could cause some problems. So selective toxicity of these antibiotics, it will depend on several factors, but again, if it's real sleek, there we go. All right, so the first group of drugs we're going to call the aminoglycoside group. And these guys, they are protein synthesis inhibitors, but they are broad spectrum, they're broad spectrum, but they will kill. They are actually the only protein synthesis inhibitors that I will talk about that will actually kill. Actually, they're very unique in that respect. So they're bactericidal. Okay. Again, they attack the ribosome, just FYI. If your bacteria or if your pathogen that you're doing your paper on, if it's treated with something called gentamicin or streptomycin, those are aminoglycosides, and the target is the 50S portion of the ribosome. The reason it is bactericidal is that it will also attack membranes. Yeah. So this is pretty toxic because, yeah, the bacterial cell has membranes, but so do we. The drug, even though a little wonky, looks pretty sleekish, right? Very race car-ish. Yeah, it'll get in there. It'll get into tissue and do quite the job. So the two examples of aminoglycosides include streptomycin and gentamicin. Gentamycin's in red, so that will be my example of aminoglycosides on the test. Little side note, even though they're broad spectrum, gentamicin is used only to treat for aerobic bacterial infections only. So here's the problem with aminoglycosides. So if you have a patient on one of these drugs, it can cause hearing loss and basically loss of kidney function. So these drugs are ototoxic and nephrotoxic. And here's the deal, they're also cumulative, meaning that if you take these drugs a lot throughout your life, at some point it will reach a certain concentration that will cause hearing loss, and again, be toxic to your kidneys. When I was at a traveler's clinic some years ago, there was a gentleman that I was talking to, and he said, "Oh, I can't hear in that ear. Took some drugs in the military, and ever since then, I can't hear out of that ear." And I said, "Did you take streptomycin?" And he said, "Yes, I did." And I said, "Ah, yeah, it has that little tendency." So you get a little infection, and the next thing you know, you've lost your hearing or lost your kidneys. All right, the next group, the tetracycline group. So, tetracyclines, this is a big generic group, and it includes such drugs as doxycycline and minocycline. People take minocycline a lot of the time for acne breakouts, as well as if you get rosacea, which I do get rosacea, and occasionally I have to take minocycline, which I hate having to take. But doxycycline is the drug that I want you to know for the test. So, this is something you would use to go after intracellular bacteria. Oh, like the one that causes Rocky Mountain spotted fever. So, the bacteria get into the cells, you take doxycycline. What is the target? It goes after the transfer RNA. It blocks the transfer RNA, so it can't bring in amino acids. So, no translation of proteins. Well, these are protein synthesis inhibitors. Look at the structure. Does this not look like a race car? Like it would get through deep tissue and into a cell, through through our cell membranes to go and get bacteria. Yes, it will. But it has some problems. But yeah, so it is very broad spectrum. It looks like it. It gets in to kill intracellular bacteria. Great for Rocky Mountain spotted fever and also used for acne. That would be mostly minocycline. Some problems associated with this very broad spectrum drug. Okay, so it is a hormone disruptor. Um, so if let's say you're relying on birth control because you'd rather not get pregnant while in nursing school. Well, if the doctor puts you on a doxycycline or a tetracycline, there's a chance you're going to get pregnant. And also, it will disrupt your hormone levels in other ways. And we females, we know what that can cause. Also, tetracyclines depress the immune response. So, your patient, if they're on this, they might be ironically prone to getting other infectious diseases. So, something that maybe the doxycycline isn't going to cover. Also, while taking this drug, it will bind to iron, so it can cause anemia. You will never want to take this drug while you are taking iron. You want to separate that out. So if you maybe take, iron first and then later on, some hours later, take doxycycline. These drugs do concentrate in bones and teeth. And while this isn't a big deal in an adult, it is a very big deal in a developing child or in a mother with a developing fetus. So we do not give this drug to pregnant women or to young children. So, because it will deposit in the growing bones, it can hurt the developing fetus. In the young children whose permanent teeth are coming in, it will cause this graying effect. Now, I had a patient some years back, and her teeth all looked like this. There is nothing you can do about it. This adult was given tetracyclines as a young child, and this is the way the teeth will look unless they put caps on them. There's nothing else you can do. There is another problem with tetracyclines, and that is that it causes photosensitivity. So if you're taking tetracyclines, you need to stay out of the sun. And if you get a weird rash, well, okay, well, it's because of your tetracycline and photosensitivity. I have a KFC photosensitivity story. So, a friend of mine who was doing research with me, later on, he got his PhD at Creighton in antimicrobials and gram negative bacteria. That was kind of his big thing. So, he was a runner and he got a horrible rash, and he went to one of the attendant, one of the not postdocs, um, one of the doctors that he was studying to become an infectious disease MD. Sorry, it escaped me. But anyway, so the doctor said, hey, well, are you taking antibiotics? And my friend went, "Ah, please, I know what an antibiotic rash is, and I would, if I was taking antibiotics, I'd know better." And he says, well, have you been eating a lot of fast food chicken lately, like KFC down the street? Now, my friend Phil, although a healthy runner, did eat a lot of fried chicken because he loved it. And the problem is, we poured tons and tons of antibiotics in the feed animals that we consume. Some of those antibiotics are still in the tissue of those animals when we consume them. And of all the feed animals, of all the animals that we raise, we put the most antibiotics into the chickens and the turkeys. So, yes, so with your bucket, you get a little extra antibiotic in there. Um, which is why, thank goodness, we're starting to go back to raising our animals without antibiotics. Europe has stopped it years ago. Fast food restaurants, they have to lead the way, and they're starting to do so because look at all the problems. And these are the ones that we know about and the ones that are well advertised. So, all right, another drug. This one's called chloramphenicol, the one that looks like the Starship Enterprise. This one also is very broad spectrum. Like the Starship Enterprise, it can go anywhere, deep space, or deep tissue, or intracellularly. This was tabled for a while, but it has been brought back to the United States since. It was not used for a while because of certain problems, and here they are. This one can get in and hurt mitochondrial ribosomes. So, not just the bacterial ribosomes, but while they're going after bacteria, it'll hurt our mitochondria ribosomes. So, patients on chloramphenicol might vomit, get green stools, and produce gray skin, all of which will be shocking. The most horrible aspect of this is gray baby syndrome. So, a pregnant woman that is exposed to chloramphenicol, the baby might be born with gray baby syndrome. This is not good. But what's really bad about this particular drug is that it is idiopathic. Idiopathic means you cannot tell when and where it will cause pathology. Okay, so we can give this drug to a patient and say, it might be toxic to your bone marrow. We couldn't tell you when that's going to happen. It's not, sometimes you can tell by age group or if they're on other drugs or they have predisposing medical conditions. We would say, oh, yeah, there's a higher risk for those people. Can't tell with this drug. It's random. So, okay, because this can get into mitochondria, it can really get in and hurt bone marrow that's always churning out new blood cells and can cause aplastic anemia in 1 in 20,000 patients that are treated. Um, and I remember when first I heard that from Dr. Ken Thompson from Creighton, I thought that is horrible. And he proceeded to also tell another case story. So there was a gentleman. It wasn't in this country, but he had a cold and not understanding what a virus was. He thought a germ is a germ and a germ is a germ. And he went into the quote unquote medicine cabinet, basically. And he knew that his daughter was treated with chloramphenicol or with an antibiotic. And because she started to feel better, she didn't finish the prescription. And there were a few extras there. Now, my mom used to do this too to save money. Hey, we might be able to use this a little bit later on, which is bad. But so he thought, okay, for my my cold, I'm going to take this antibiotic. He took one pill. He died. He died of aplastic anemia. It's idiopathic. You don't know. You don't know. One other story about this. Some years ago in China, their bee population was dying, and poor bees. They found, though, the scientists in China found that that there were bacteria that were infecting the hives. So they thought, well, okay, so let's kill the bacteria. What should we do? Let's find an antibiotic that is very broad spectrum, and we'll just hose down the hives with chloramphenicol, which they did. And so it got into the honey combs. The not only the honey was loaded with it, but also the other products that come from bees and beehives. And it was shipped throughout Europe. And keep in mind, this is idiopathic, these chemicals. So, are you beginning to understand why you have to treat all antimicrobials with respect, right? Okay. Let's talk about the macrolide group of antimicrobials. These are still protein synthesis inhibitors. I still have the ribosome up there. You can see that this is a little bulky. It's not as broad spectrum. It's not really something you're going to go use to go after intracellular bacteria, but it's pretty good. It goes after the big 50S portion of the ribosome in our bacteria. Our examples, I have two because they're so commonly used. Both of these examples, really. The first one is known as erythromycin. This is the one most often prescribed when a patient can't take penicillin. It could be that the patient has resistant bacteria and the penicillin weren't working on the bacteria, so you give them erythromycin. Also, it's most often used in patients who are allergic to penicillins. This is tremendous. This is nicely broad spectrum, so there you go. But it also, oh, little side note to this one. Sorry. Little side note, this will cause some diarrhea, or it can be quite severe as it takes out a lot of your normal microbiota. It can also give you a tummy upset, like ulcers. It feels like an ulcer. Clarithromycin, it's not in red, but it is a macrolide. This one has fewer gastrointestinal problems, but there is a metallic taste that you get with this one. So, because I don't respond well, my GI system hates erythromycin. Usually, I end up with clarithromycin. Now, the last one, also in red, this one you need to know then, is Zithromax or azithromycin or Z-Pak. Everybody loves this because, well, it's better for compliance. Really, you're kind of doing your 5 doses and you're done. So everybody kind of likes Z-Pak. What does Z-Pak do? It blocks the 50S portion of the ribosome. So what does it stop? Protein synthesis, right? Translation. Very good. All right. So, time for a quiz. All right, let's do this. Which of the following is not a beta-lactam drug? Cephalosporin, ampicillin, penicillin, azithromycin, carbapenems. Of course, azithromycin, right? All the rest of these. The cephalosporins is there. The cillins, the penicillins are there. And then the carbapenems are there. Very good. Who discovered penicillin? Alexander Fleming. That is right, not Robert Penicillin. All right. Which inhibits bacterial cell wall synthesis? Penicillin, ampicillin, vancomycin, bacitracin. Of course, all of the above. E is correct. Sulfa drugs. Okay, the sulfa drug. Remember, these drugs are going to stop folic acid production. They have pretty good selective toxicity because for us, well, we can consume our folic acid or folate. Okay, so we're pretty good there. Here, what happens is there's an enzyme that converts PABA into folate, okay, folic acid, but the sulfa drugs like sulfonamides will block it and work as a competitive inhibitor. So they block paraminobenzoic acid, that's what PABA is. That's the normal substrate. It's supposed to go in and go into the enzyme, and the enzyme converts it to folate. Okay. If the bacterial cell can't get folate through diet, and they can't, then they're going to be in trouble. So we can absorb folate from the food we eat, but this is pretty much the only way bacteria normally can get their folate. Without folate, the bacterial cells can't make new DNA. Without DNA, the bacterial cells can't replicate. Huh. Okay, that's pretty good. So pretty good selective toxicity. Still not as good as the beta-lactam drugs, and there is a lot of photosensitivity there. So, by the way, just when women are when they're pregnant, they want you to take a lot of folic acid, right? And well, that's because they're the baby, the fetus is just tons of newly made cells, and the more cells you make, you're going to need new DNA for all the new cells. So you're going to need folic acid to make your DNA. Okay, that's why. All right, the example of the sulfa drugs, sulfonamides, and this includes trimethoprim. And again, it's a competitive inhibitor. It undergoes competitive inhibition. All right. Little side note here, I did want to mention that sulfa drugs that are folic acid, folate synthesis inhibitors also will attack protozoans, interestingly enough. So, yes, they'll go after bacterial cells, but also protozoan cells. So, this, if you're looking at these red blood cells, well, this looks weird. That's because they are full of the little protozoan parasite that causes malaria, plasmodium, actually. So, we can use sulfadiazine to kill these little malaria parasites. And this is Toxoplasma gondii, causes toxoplasmosis, the reason we don't let pregnant women clean litter boxes. So this drug will attack these protozoan pathogens. So yay. But okay, you didn't need to know that for the test, but there you go. All right. So, some more questions. If your patient is allergic to penicillins, which particular antimicrobial should they stay away from? K-Flex is azithromycin, tetracycline, erythromycin, Flagyl. Okay, we haven't talked about Flagyl yet, but K-Flex is a cephalosporin, right? I know I tricked you a little bit there, but okay. These, okay, are all protein synthesis inhibitors anyway. Flagyl, I'll talk about that one coming up. All right. So we're going to leave the protein synthesis inhibitors behind, right? So the first group, those were the cell wall synthesis inhibitors, beta-lactam drugs like penicillins, cephalosporins, carbapenems, vancomycin. Then we went to the protein synthesis inhibitors, right? We went to the aminoglycosides, which actually will kill. And we talked about tetracyclines, and we talked about, the macrolides like Z-Pak and erythromycin, and chloramphenicol, patooey. All right. And then we talked about sulfa drugs that stop the production of folic acid, but there's another group of drugs, another class. These are going to stop nucleic acid synthesis. So it's going to stop DNA production as well as RNA production. This big class of group is known as the fluoroquinolones. Now, in the clinic, you might see a physician just abbreviate this as FQ. FQ, you can tell they probably don't want to spell fluoroquinolone. They may have forgot. But anyway, fluoroquinolone, now it's easier. Anyway, so these drugs actually were discovered in the 1930s. The first ones were very toxic. When the laboratories discovered these, they were actually looking for cures to malaria. But they found out, this works on bacteria actually. So again, the fluoroquinolones, they are completely synthetic, meaning they are completely outrageously priced. Anything synthetic is very expensive. So, and probably, well, we'll just say expensive. This is going to target DNA gyrase topoisomerase 4. Remember those. So those particular enzymes help DNA when it is unraveling, either for DNA replication or transcription. Okay. So the DNA cannot replicate without breaking if these enzymes are blocked. Because remember what happens, the enzyme will help disconnect and reconnect the double helix as it unwinds. Otherwise, it will break. But with the fluoroquinolone there, yeah, DNA is going to go snap, snap, snap. These do come in generations. The first generation was norfloxacin, pretty toxic. Second generation, ciprofloxacin. This one, Cipro, you're probably familiar with Cipro. Most commonly used against gram negatives, but not always. It is broad spectrum. And levaquin, okay? Levaquin usually used against gram positives. Now, Cipro, when this came out, they gave it to everybody. So, okay, we have a whole environment full of bacteria, and they are exposed to different concentrations of Cipro. Some of them had a random accidental mutation, and yes, there is Cipro resistance out there, and it's booming actually because the overuse of Cipro was booming. So, Levaquin, interestingly enough, there's not a lot of resistance against this, and here is why. So I have the no kitties, no resistance so far. Well, it is out there, but it's not strong resistance. So here's the little one. We love our children, and they are adorable. And we really don't care that they are walking, talking little germ factories because they are little incubators. Their hygiene isn't terrific, and they kind of ingest everything that they can get their hands on. They're into everything. They just are, and they're really good at sharing germs. So little kids are constantly on all kinds of antibiotics, always, like the amoxicillin and other forms. So unfortunately, they have been also little breeding grounds for antibiotic resistant bacteria. Now, Levaquin is not prescribed to children because there was some research some years ago on animal models like mice, and they found that it had some neuromuscular toxicity. So they said not for the kids can't have it. And also that we haven't abused these drugs, so they're still pretty strong out there. There's a third generation, moxifloxacin. I just love saying moxifloxacin. So that one is used, but again, it's not let out. Usually it's only in hospitals. We don't want it out there. We don't want it in a feed lot so that bacteria have lots of opportunities to find mutations against it. So problems with fluoroquinolones. They are extraordinarily broad spectrum, very powerful. But like I said, the bacteria have developed resistance against Cipro. The toxicity can be very high in some individuals. They can cause cardiovascular problems, nervous system, neuropathies, and a lot more. So some people, if you go on the web, they really had some bad side effects against the fluoroquinolones. But what they have to, well, and hopefully they were never given a fluoroquinolone unless they absolutely needed it. The nice thing about fluoroquinolones is that they are broad spectrum. They will go in and get a pathogen, but you want to treat them with great respect and never take them unless you have to take them. Like maybe you're exposed to anthrax, literally. Okay, then you can have your Cipro. But yeah, big toxicity problems. All right, now I'm going to switch gears a little bit and talk just a little bit about the kinds of drugs that we give people who have protozoan diseases. So, for example, if a patient has toxoplasmosis, all right, this might be something that we give them, or trick, or giardiasis, also known as beaver fever, which you will be exposed to later on. But okay, so there are other quinolone drugs out there, not fluoroquinolones, but just quinolones, and they are used to basically treat protozoans, not bacteria, but protozoans. They have pretty much the same action. They're going to affect the topoisomerase enzymes. I can talk. that help the uncoiling of DNA during replication. So, if you're going traveling or you're doing missionary work, you might be going into areas where malaria is a problem and you might be prescribed mefloquine. Unfortunately, it does cause psychotic disorders, but so if you ever go on mefloquine, there are possible problems. I know. Shining, The Shining from the movie The Shining. I myself, I'm a sleepwalker. I cannot take mefloquine. A friend of mine and I was going to the rainforest of Ecuador, and I can't take that drug. Friend of mine also found out that he can't. When he was on safari, he thought lions were attacking his tent, and he thought the middle pole to the tent was a spear, and he was going to personally fight off the lions. Yes, you can imagine. All right. Now, here is a drug that you might come across. Now, this is used quite a lot. If your patient had stomach ulcers, Helicobacter pylori, they may have been given metronidazole, or if they have another gram-negative problem, maybe C. diff, they're given metronidazole. Um, if you have puppies or kittens, they tend to have all kinds of protozoan and bacterial problems, and the vet will just give them metronidazole. By the way, it comes by another name, Flagyl, and that's usually what the kittens and puppies get. But metronidazole. Metronidazole is a very weird drug, and I'll try to explain it as best I can. It does have varied uses. The chemical itself is not the active form. Literally, the drug has to enter the cells, okay, the cells of the bacteria or the cells of the protozoan, and inside the pathogen cell, the pathogen itself will convert the chemical and convert it into, and so we call it a metabolite drug. And what it makes, so it's broken down into something toxic to the bacterial cell, and that itself will break the DNA. So it attacks DNA. Specifically used for anaerobic bacteria, so anaerobic metabolisms, and that's why it's given sometimes to, like something like, oh, just said it not too long ago, Helicobacter pylori. Let's just say it's more effective to anaerobic metabolisms. So, yep, we give it to bacteria and protozoans. So here are a couple of examples of the protozoans. This is Giardia lamblia that causes giardiasis, also known to campers as beaver fever. All right, the next guy, this one here, this is known as trick, but actually it's Trichomonas vaginalis. So this is another reason for these are protozoans that you might be treated with metronidazole. Okay. All right, now we're going to move to the last category. This is the most scary category. These are the cell membrane disruptors. Now, the drugs that I'm going to describe, again, some of them are systemic, some of them are topical. The topical are going to be that tends to be the safest. But remember that all cells have membranes. Yes, fungal organisms will have a membrane we can disrupt, and bacteria have membranes we can disrupt and we can control them. But we also have membranes, and most of these drugs will hurt the pathogens in some way more. So it's more toxic to them than to us. Okay? Some of these drugs are getting a little better, but a lot of them are still pretty bad. Okay, the advantages why use them. The microbes don't have to be actively dividing, which is what you have to have happen with cell wall synthesis inhibitors. Okay, these will bind right to cell membrane phospholipids and sometimes proteins or other structures. They destroy selective permeability. Literally, the cell can't control what goes in and out. So the cell will lyse and die. So they're very bactericidal. I'm talking like Rain Man. I'm a very, very, very good driver. Okay, disadvantages of cell membrane disruptors. We also have membranes. The drugs target the pathogen membranes more, if we like that. And this is what we tend to turn to, by the way, if our gram-negative pathogen cannot be killed by carbapenems. Yeah. So remember Pseudomonas aeruginosa, my brother died from this, right? Or Klebsiella pneumonia, or E. coli, or one of the many other gram-negatives that we don't have time to talk about. If carbapenems aren't working, this is all we have. Okay? Some of these drugs are so toxic, like I said, we took them off the shelf until we had no choice. So this is an example of what these drugs can do. They can, again, disrupt the semi-permeable membrane of our pathogen, and hopefully only the pathogen, but there's probably a few of our cells that take a hit too. This is Pseudomonas aeruginosa. So again, there's a double membrane that Pseudomonas has, and this will go through and make it very leaky. Okay. So examples of cell membrane disruptors, the first one is polymyxin B, and that's actually where this image came from, is it's the action of polymyxin B. Polymyxin B typically, this is what we use for gram negatives. It loves to go after the LPS and that freakish outer membrane. And again, for Pseudomonas aeruginosa, Klebsiella pneumonia, if nothing else works, we use polymyxin B. Okay. Toxic to other membranes, human cells too. It is nephrotoxic. It is neurotoxic. So goes after the nerves, goes after the kidneys. It is cumulative. Now, if you're thinking, well, thank goodness, I'm just never going to use this. Well, look around. If you're not using bacitracin, chances are you're using um, some chemical on your wound that has polymyxin B. I would try finding something that doesn't have it. I know I've tried. Okay. Uh, do not use these chemicals unless you absolutely need them. Okay, wash your hands with soap and water. If you don't have a really big raging infection or a big surgical wound, soap and water, you know. So clean it off, blot it dry, cover it loosely. Okay. If you're healthy and reasonably, no big infection is showing up, don't use this stuff. I won't have it in my house. Okay. There are times when you do have to use these after a surgical wound. If you've had a biopsy, maybe you have to use this. I would especially not use this if I could, if the wound was still bleeding. Okay. All right. Amphotericin B. It has an action like nystatin. Both of these are used for systemic fungal infections. The target is a structure known as ergosterol. Ergosterols are only found in fungal membranes. The drug will take ergosterol and turn it into a pore. So it's kind of interesting. So the drug comes in, and this would be the fungal membrane, semi-permeable membrane. And to stabilize the membrane, they have ergosterols. Ergosterols, we don't have these. We have cholesterol. We don't have this. Fungal organisms do. So amphotericin B attaches more to ergosterols than they do to our sterols, and they form a pore. And again, that's going to ruin semi-permeability and kill the cell. Okay. The membrane loses permeability, cell death is the result, right? Sometimes we give this to people who have also raging cases of yeast infections. Okay. So here I have the thrush to show you this is Candida albicans. Okay. And because it is, it does have toxicity issues. It is toxic to mammal, mostly the liver cells. So you want to have the blood monitored the whole time. Okay, so I also wanted to talk about another cell membrane disruptor. This one I'm not going to hold you responsible for, but actually the next two are so commonly used that I had to mention these. So that way, if you're wondering, well, how does Lamisil work or the active ingredient known as terbinafine? Well, I thought I would take a moment to answer that question. And another one coming up. So again, it targets the membrane. This drug is loves the lipids. It's very good at getting into fatty tissue and nails. So we use this a lot if you have an infected nail. Like you went to get a pedicure or a manicure, and then all of a sudden you have a fungal infection deep in the nail bed. So this is something that we would give. Now, you wouldn't use this topically, but if used orally, this can be very toxic to your liver. Usually it will take about 6 months or so, and we give it only in small doses. There are over-the-counter types of Lamisil. We give this to, like people who have, again, yeast infections, jock itch, so forth, or if they have, another version of a fungal infection would be if you had athlete's foot. Lamisil is one of those things that you would use for that. Okay. Another FYI, and I bring this up only because monostat is one of the major antifungals that is used, especially by us as women. So I thought, okay, I needed to mention what this does. But the action is pretty, it was just something that they just discovered. It actually goes after what's called the cytochrome system in the mitochondria. The the mitochondria, this is the powerhouse of the cell. There's a lot of machinery that makes ATP here, and that's what monostat does, and it tends to go after fungal mitochondria more. Okay, so and this is if you block the P450 cytochrome system, then the fungal cell is unable to make ergosterol very well. All right. So another name for monostat is miconazole or azoles in general. All right, finally, let's talk about parasitic worms and other multicellular animal parasites. So for these guys, okay, so let's talk about killing worms. Worms are helminths, and so the drugs are called antihelminthic drugs. I can talk. The main one that I want to talk about is ivermectin. Ivermectin will cause the parasitic worm, to be paralyzed in the esophagus. So it's esophageal paralysis. Something you should know about worms and other small animals is that they have to constantly feed. So adult worms and insects will starve to death in about 24 hours. And after that, the adults will die. Now, I should tell you, so over here, we have a goat being dewormed, and a lot of the drugs are ivermectin based. If you're thinking, cool, well, then they're all dead in 24 hours. I don't have to worry about it. Well, worms and insects also lay eggs. So we tend to keep this drug up and going, and, so that the drug is in the system when eggs hatch. Just so you know, ivermectin does come from bacteria, bacteria that don't like worms and I guess worms eating them and insects eating them. This drug also works on outside parasites or ectoparasites like mites. So if you have somebody who has mite allergies or maybe the mites on the skin are causing a big flare up, and mites are everywhere. There are also some species of mites that cause scabies. So you could use ivermectin for that. You can use it for head lice as well. And this is just to show you this particular kind of mite causes scabies and they burrow under the skin and lay eggs. So you've got to kind of keep the ivermectin up. And then lice. Okay, head lice. Typically we don't see body lice very much, but yeah, lice. Something kind of cute, FYI. Here are some old remedies. And if you have any family members that grew up on farms, maybe you know of some of these old-fashioned remedies. For example, they used to give tobacco, basically the nicotine, to kill parasitic worms in livestock. The drawback, I know, take a pause. The drawback is, well, yeah, it would work, but the selective toxicity is bad. So if you got the nicotine levels up high enough to kill the worms, it would kill the host as well. So it would kill the parasitic worms, but also, okay, kitty there. Copper sulfate, and again, you do not need to know any of these. They used to use these for sheep, but again, it was toxic to the sheep, so selective toxicity was poor. Copper oxide used in sheep and goats, still under investigation, I guess. It didn't absorb into the host cells so much, so therefore it isn't as toxic to our host cells. We're not sure why it works. They would use there's herbs that are out there that are supposed to kill worms, and one herb is called wormwood because it's supposed to kill parasitic worms. But again, yes, if you had it in such a high concentration that the worms would die, well, so would the host. This is what wormwood looks like if you want to know. Pumpkin seed and garlic, please. That's pretty lame. Sometimes they would use little pieces of diatomaceous earth. It's like little microscopic glass creatures. They've died and they've left their cell walls behind, which are glass. Some evidence says that, okay, if you give it to your livestock animal, the worms will try to eat it and it will hurt the worm's digestive tract. Maybe. Okay, let's do some questions before we go into the next section. Just as a review, which of the following is a true antibiotic by definition? Penicillin, fluoroquinolone, levaquin, ciprofloxacin, or all of the above? Only penicillin, the beta-lactam drug, right? Fluoroquinolones include levaquin and ciprofloxacin. So these are both the same class, and that class is fluoroquinolones. They are artificial, completely synthetic. Doripenem is a chemotherapeutic agent that attacks cell wall synthesis. It is one of the few antimicrobials that we have left to treat tough gram-negative pathogens. Based on the name alone, which group of antimicrobials does it belong to? Cephalosporins, carbapenems, penicillin, vancomycin, isoniazid. Of course, B, carbapenems, M&M and M&Ms. Okay. Which of the following chemotherapeutics attacks cell wall synthesis, is chemically large, is narrow spectrum, and only kills gram-positive bacteria, and is used to treat MRSA? My goodness, that was a mouthful. Attacks cell wall synthesis, large, narrow spectrum gram-positives. Yeah, of course, it's Vanc. E, Vanc. Okay. This one inhibits bacterial protein synthesis. It is very broad spectrum. It really gets into cells and tissues to kill bacteria. However, it can inhibit birth control efficacy and depress the immune system. A, vancomycin, B, tetracycline, C, penicillin, D, sulfonamides, E, polymyxin B. Of course, it's B, tetracyclines, and causes photosensitivity as well. This expensive antibiotic can cause red man syndrome if infused too rapidly. Azithromycin, flagyl, gentamicin, vancomycin, chloramphenicol. Of course, it's Vanc, big V. Which of the following would you use to target a fungal membrane ergosterol? Penicillin, vancomycin, chloramphenicol, amphotericin B, carbapenem. Of course, that's your D, amphotericin B. Erythromycin, what is that going to go after? What process? Nucleic acid synthesis, like DNA and RNA. Protein synthesis, or it's going to go after the plasma membrane, or cell wall synthesis. Of course, it's protein synthesis. Translation. All right. Now, Of course, there are a lot of consequences to taking antimicrobials inappropriately, and we will get to that. But now let's talk about consequences of taking antimicrobials appropriately, not even thinking of side effects, okay? Not thinking of side effects of the drugs. All drugs have side effects. But let's talk about some other things that come up, okay? Okay, so super infections. Now, here I have just the GI tract. I don't have, we're not going to talk about the drugs and how they leave the intestines and how they travel through the circulatory system, how they go through the liver and all of that. Um, we'll just talk about how the drug affects the GI tract and your normal microbiota in the GI tract. But of course, this is relevant throughout the whole body. Okay. So let's suppose your patient is prescribed an antibiotic, and there it is. So it goes sweeping through your GI tract, which has the most normal microbiota, and they're there and they're training your immune system and they're giving you vitamin K and they're doing a lot of other very good things. And okay, along comes this antibiotic. Let's say it's broad spectrum. And oh, yeah, but some bacteria are more resistant than others. So, boop, 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 boop. Ah, what's left? Oh, that would be like the endospore formers. Okay, little endospores. And what are the hardest things to kill? Yeah, endospores. Who makes endospores? Oh, something like Clostridium difficile, C. diff. As a result, they're left behind. They have all the resources. They don't have to fight. They don't have to compete. They're not getting all kinds of chemical weapons thrown at them from other bacteria. So they're going to take over. Okay. And as a consequence, and here they are, they take over, and you get a condition like this, pseudomembranous colitis, which your patient can die from. Okay. As I mentioned, my brother, two things killed him: resistant Pseudomonas aeruginosa and C. diff. Okay. So this is necrosis and perforated distal ileum due to C. diff. And you can see everything just red and just angry as all get out. And when perforation occurs, you're going to get sepsis. This is bad. All right. So again, and the patient, just backing up, this is if your patient's taking an antibiotic that they should have taken. Okay? So they took a broad spectrum because they did what they were supposed to do. And maybe it was to kill bacteria in the bladder or the lungs or something like that, but you get a super infection. All right, so let's suppose your patient is prescribed an antibiotic again. Okay. And but before this happens, the bacteria living in your gut and they're frolicking and they're eating and they're replicating. They're going through a lot of binary fission. And one has a little mutation. One little daughter cell is born, hello, with a little genetic mutation. Now, she may not be as strong as her brothers and sisters, but she's okay. And, mutations, sometimes they can be harmful, but she's all right. Sometimes they have absolutely no impact. And right now, this does not have any impact. It just doesn't have any effect at all. Sometimes it's beneficial. Remember, this is random. This did not occur as a result of an antibiotic. It just kind of happened. Now, the antibiotic goes through, and it turns out the little mutation she had, hello, makes her resistant to that antibiotic. And everyone else dies, and she grows, and she has her own daughter cells. They have daughter cells, and they have daughter cells. And that resistance gene is passed to all the new offspring, all of her daughter cells. Okay? So they all carry this resistance. And now you have a superbug. Okay? So that drug will not work. Okay? And the superbugs can end up just anywhere, not just in a human colon. This could happen in a cow. or a chicken or something like that. And golly, it could get on some beef that didn't get cooked all the way. And then it got consumed. And then it comes out the GI tract. And it can be found everywhere, everywhere, everywhere. Resistant bacteria, everywhere. Okay, everywhere. Hopefully not there. Okay. Oh, let's suppose your patient is prescribed an antibiotic. Here we are. Now I've included something other than bacteria. Your normal microbiota also includes many different kinds of yeast, represented by these little gray circles that look like they have a little head on them. These are budding yeast, little yellow Y for yeast. Okay. So this is an antibiotic. Let's say it's a beta-lactam drug, or it is a 70S ribosome protein synthesis inhibitor, or something like that. And it's broad spectrum and it kills everything but the yeast. Why not the yeast? Yeast are not bacteria, they're fungal. They're like us. And now you just destroyed the normal microbiota of bacteria. What's left? Yeast. And then your patient gets a yeast infection. Again, keep in mind, not all microbes are created equal. Your normal microbiota is essential for good health and balance. Okay? So this is another reason it's better not to give a broad spectrum if you can. Let's say the only guy causing the problem was a Staphylococcus aureus. So you could probably knock that out with maybe a beta-lactam drug. Okay, leaving all the other good normal microbiota behind. Okay, well, since these are resistant, then maybe we'll go with a carbapenem. Okay, we're back to this image. Again, think of the family that I know of that goes and picks up their drugs. They literally have black garbage bags, lawn bags full of drugs. They bring them back. And I understand. What do you do when you need meds and you can't afford it? But I can see if you know your drug, you know your dosage, you know how you're supposed to take it, and your doctor has already said, okay, take this. I can kind of get that. But unfortunately, people really abuse these antibiotics way too much. And antimicrobials have been abused, even though it's getting better in this country. Throughout the world, there's still a global problem. Let's just put it that way, which I'll talk about that in a minute. Imagine a world without antimicrobial medications. You've never known that world, and really neither have I. I used to get earaches, and I could always get a shot of penicillin. Penicillin G, I always knew it was penicillin G as in G that hurts. But yeah, I always had the ability to get an antibiotic and I was fine. But we now experience complete clinical failure when trying to treat patients with bacterial infections. I mean, complete clinical failure. So that means that we have to well, we're kind of going back into time. And how bad was it back then before antibiotics? Well, so my grandmother, though, if you said that I had a strep infection, she would flip out. She knew that infants that had strep as a diagnosis probably wouldn't survive. Okay. There was a good chance you wouldn't have pulled through that. Your baby would not have pulled through a strep infection, possibly not staph either. So, yeah, prognosis for staph or strep infections before the 1940s, which is when we just started to use penicillins, it was not good. So, and let me just back up just for a second. Think of all the procedures you can't do if you don't have a good working antibiotic. You can't have oral surgery, right? Yeah, because you need like an antibiotic prophylactically. Um, Hip and knee joint replacement, can't do that. Nope, can't do that. Transplants, nope. Gallbladder removed, not so much. Basically, everything shuts down. We're in, that's, it's very serious when that happens. Um, Misuse coupled with evolution of microbial resistance does threaten these medications. We don't have a lot of medications to use, especially against the gram negatives. So we have to be very, very careful with how we use these antibiotics. And maybe we can also just be really careful about the spread of bacteria as well. So infection controls, right? Infection control. And like I said, current bacterial resistance is causing complete clinical failure of all antibiotics. I have some notes from Dr. Nancy Hansen, who is a Creighton professor, and she was delivering some startling statistics, and I knew it was bad, but this did make me sit back. It probably will with you as well. So we get about 2 million antibiotic resistant infections every year in the US, every year. And even if patients are treated successfully, there's a chance they're still colonized by these resistant bacteria. Um, and we see about 23,000 deaths every year in the US. And like I said, my brother was one of those cases. To let you know, the United Nations had a General Assembly in New York City in 2016. This is the fourth time in history that they have met over a global health problem, and that is the antibiotic resistance global health problem. Just to give you an idea, uh, they did some modeling, some computer modeling, and this is what they came up with. This is the world you're looking at in 2050. So when it comes to when it comes to deaths every year due to antimicrobial resistance, we're probably looking here in the United States 317,000 deaths every year. Latin America, a little higher, 392,000 deaths. Europe, a little higher still, 390,000. When it comes to Africa, 4,150,000 cases every year. Asia, 4,730,000 cases every year. The only place that's pretty much looking fairly normal is this little place here called Australia. And it would probably include New Zealand and Tasmania. 22,000. Why? Well, it's funny. One of my colleagues, I read these statistics to Mrs. Shives, who said, oh, yeah, because they're really good about monitoring their health care and they don't abuse antibiotics. I was so proud. I thought, good for her. Very clever lady. But yeah, because they have always monitored their antibiotic and other drug use. They're very, very cautious. Africa and Asia, not so much. And if you don't think this won't affect us, of course it will. So it is a global health crisis. All right, so let's just stop for a moment and look at how the bacteria are doing this. So first of all, think way back when I said that bacteria have been known to manufacture little enzymes and they send them out into the environment. So these are little exoenzymes. Here, Pac-Man, yes. So these are little exoenzymes made by bacteria and they are sent out into the entire environment. And what these little enzymes will do is they will munch up drugs like beta-lactam drugs. So these enzymes are known as beta-lactamases. Okay? So when we had our bacteria resistant to the penicillins, the bacteria made little penicillinases. Okay? That ate up all the penicillins. This was bad. And then bacteria that had penicillinases acquired a new mutation that would make another enzyme that would munch up cephalosporins. So now the bacteria were making penicillinases and cephalosporinases. That's really bad. So then the bacteria acquired a third type of mutation, And so they not only had penicillinases, but cephalosporinases, but they also made carbapenemases. This is, this is really, 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 really holy smokes bad. And I would put an expletive there. Okay, so this would include your KPC. This is a let's freak out kind of organism. If this is remember it's Klebsiella pneumoniae carbapenemase producer. There's also this one, NDM. That's another really, really bad one. I won't ask on a test. So really, the bacteria that have enzymes that really can take out penicillin, cephalosporins, and carbapenems, really we just say they're beta-lactamase producers in general. Basically, they make enzymes that knock out every beta-lactam drug. And remember, with gram negatives, you only have the really toxic drugs to take care of you. So this is what's happening. So let's say we added penicillin and the bacteria aren't exploding. Why? Because there's little penicillinases taking care of penicillin. So the bacteria are happy, the cell walls are being made, the PBPs are safe. The penicillin isn't getting to them. Okay, so how are they getting antibiotic resistance or acquired resistance? Again, it usually starts off with a spontaneous mutation. The bacteria cannot just all of a sudden decide to make a mutation. Okay, they do not respond to the antibiotics by mutating. No, that's not how it works. It's random. But the antibiotics will select for the antibiotic resistant strains. By the way, this is Enterococcus faecium, just so you know. So if a bacterial cell doesn't get a spontaneous mutation of their own, they can actually acquire new genes from other species. And that's what I talked about earlier. So you have enterococci bacteria like Enterococcus faecium developed a resistant gene, resistance genes against vancomycin, and now this is VRE, vancomycin resistant enterococci. And then, well, they shared some of the genes with Staphylococcus aureus. So now you have vancomycin resistant Staphylococcus aureus, or VISA, remember? And the gene got to Streptococcus pneumonia as well. So on and on and on, because they're very related species and they always end up kind of in the same area. Whenever you have bacteria stew, like in your digestive tract, or it could be on your skin or in fecal material in the sewer, in the water systems, there's opportunities for them to share genes, and they do. So, okay, mechanisms of resistance. I know this is really busy, but here's your bacterial cell. Here it has that little piece of DNA known as a plasmid. And remember, bacteria share plasmid through sex, right? And they could have multiple genes and multiple genes. Some bacteria will have 20, 40 different genes, all on one plasmid, okay? So what could one gene make? Well, we said that one gene could make penicillinases to knock out penicillin. So you make some little, something that'll just munch up the penicillin. Excuse me, sorry. They could change an outer structure. So change the structure of the target. For example, the bacteria like Staphylococcus aureus, some of them had a gene that altered the PBP enzyme. Okay, and that's how Staph aureus got methicillin resistance. Okay, antibiotic resistance gene. So that just, I know there's not a picture of PBP here. Sorry. This is a real cool one. There are genes in a lot of bacteria that manufacture or that actually change the protein pump on the outer cell surface. You know, bacteria are always making pumps, maybe to pump out waste products. But this different mutation on the plasmid makes a very unique pump. And instead of pumping out waste, it now pumps out the antibiotic. So, for example, tetracycline enters the cell and the cell spits it back out again. efflux pump. And they can also develop an alternative pathway to be able to make folate. So that is one other method. And like I said, some bacteria are carrying around genes for all of this and multiple versions of it. Okay? And when you add antibiotics to the environment, you select for the bacteria that have the mutation. I just wanted to show you probably what happened with the beta-lactamase penicillinases. So here is ampicillin, so it's a penicillin, has a beta-lactam ring. Here's our beta-lactamase, like a penicillinase, and it's going to munch up the beta-lactam ring. Okay, how did this get made? So here we have a whole bunch of bacteria. Here are their plasmids. In here is a little tiny gene. And this gene, okay, let's blow this up. Genes, here's the gene, little segment A's and T's and G's and C's, all the DNA. Okay. And this is going to code for a little enzyme. And here's the active side of the enzyme. And this is just a waste disposal enzyme. So all of these bacteria have this little gene that will manufacture little waste disposal enzymes. Waste fits into the active site and the enzyme destroys it. So this is a way for these bacteria to get rid of excess waste. Now, along comes a little accidental mutation, like I mentioned before. This bacterial cell is different than his friends. Now, there's no antibiotics here. And again, this guy isn't any weak or any stronger than anybody else. He just has a little random mutation. However, in an environment of antibiotics, then it's a little different, okay? He actually would be the strongest. Think of Darwin, strongest survival of the fittest. So little mutation now changes the protein enzyme that's made. It has a different active site. And now what fits into the active site is not waste, but okay, our antibiotic, our penicillin. Sorry about my pictures. I do the best I can. Okay. And there we go. One little mutation. And all of a sudden, voila, you have a penicillinase to protect you from any kind of penicillin coming your way. And again, this is not something they do on purpose. It's an accident. Because they can divide and double in numbers every 20 minutes, there's tons of mutations. They're accidental. But once you add drugs, oh, let's say you have a whole bunch of cows in a big feedlot, and the cows are up to their knees in mud with fecal material. And since the cows have been taking in, all of those antibiotics, there's a lot of weak antibiotic concentrations in the mud. Maybe not, maybe it's not strong enough to kill all the bacteria, but it's strong enough to kill the weakest. And then you're going to select for some of the bacteria that are somewhat resistant. And then they're left and they divide. And then, okay, then stronger antibiotics come their way. And one will accidentally have another mutation that even makes it a little even stronger and more resistant. So resistance isn't something that occurs overnight, but it can happen pretty quickly. Well, actually, it can occur overnight. Sorry, we do it in the lab all the time. But I'm just saying that if you have an environment loaded with antibiotics, you will select for those accidental mutants. Okay? So antibiotics select for the mutants. It does not cause the mutations. Antibiotics select for the mutants. It does not cause antibiotic mutations to occur. All right. So here's something that's all over the web. Resistance is futile. Methicillin resistant Staph aureus. Okay, so now let's talk about the antivirals. Now, way back when I was a kid, there were no antivirals. Antivirals came about, well, it started with all the research that we had looking at HIV, and that's when virology research had some dollars and we could learn about viruses. If you know about them, then you know how to control them better. We're still in the infancy of that, unfortunately. There aren't a lot of antivirals that are available because a lot of them are so toxic. Remember, they take over your cell, they become you. So how are you going to go in and poison them without poisoning yourself? Selective toxicity is pretty darn hard. So, for example, AZT that treats HIV, very toxic. Selective toxicity, hard. They use our cell for manufacturing and they use a lot of our stuff. So again, what are you going to do? CAZT that treats HIV viruses. We use typically three strategies to control viruses. Number one, so cause a lot of mutations in the cells where the viruses are replicating. You see, the viruses would be replicating their DNA faster because they're making more. Well, the viruses are making more DNA, so they're going to get more mutations. They're going to be hurt more or faster. Yeah, toxicity issues there. If you know about a virus, you can target unique viral structures. So if a virus has, like HIV, has reverse transcriptase enzymes, go after that. That's not something humans have, so you can target unique viral structures. Or over here, golly, we have influenza, and they have a thing called neuraminidase here. This neuraminidase allows these viruses to move in and out and through mucus to spread better. Okay. There's another way you can treat for viruses, and that is to manipulate the host's immune response. So the host will recognize that the virus is invading and do something about it. All right, so a little bit about influenza treatment. You don't need to know the failed attempts. At first, we had amantadine, where the viruses very easily developed resistance, so that didn't work. Romantadine, same thing, viruses developed resistance. Zanamivir, this was approved, but only for people that were 7 or older, and it was a neuraminidase inhibitor that could be used both for influenza A and B. Then comes oseltamivir, known as Tamiflu. Sorry. This one was approved for treatment of persons who are at least a year old. Tamiflu is again going to inhibit this little enzyme sticking out of the influenza virus called neuraminidase. So it is a neuraminidase inhibitor. Result, the virus can't leave the mucus. They get stuck. So they can't infect more cells in the host. The problem, well, it's no good unless you start treatment within about 24 hours, certainly 48 at the max, but you have to know at the onset of symptoms, you have to know that, hey, I think I have the flu. I better get tested today. And then you have to be diagnosed and get on those antivirals right away. 48 hours, it's really too late. But to get the best response, you need to figure out it's influenza and not just a cold. Get the Tamiflu and go for it and take it. That's about the only time it's really that useful. Also, especially in some older patients, it can have neuropsychiatric events. Okay. Okay. Another antiviral. Let's attack herpes viruses. So, these drugs that usually are used to attack herpes tend to be nucleic acid analogs. Oh, yeah, like AZT. Sort of. But this one is a little different. It's not as toxic as AZT. Acyclovir does look like the DNA guanine. So remember, G's with C's over here. Looks like guanine. So his DNA is being replicated. The enzyme that kind of matches everything up accidentally will put acyclovir there instead of guanosine. Okay, they look the same. They're base analogs. Okay, and that will cause mutations in the developing herpes viruses. So when we're talking about oral herpes, genital herpes, chickenpox, shingles, all of that. The reason this is not as nasty as AZT is that, well, there's a lot of interesting things that have to happen to acyclovir. And the virus actually screws up and makes acyclovir in the cell, makes the deadly form. So it's kind of interesting. It's so it's hard to explain, but just know it's not as nasty as AZT. Okay, but still, you don't want to abuse it. So I would, I'm not crazy about any antivirals, but Abreva is a cyclovir that you put on just topically. So if you get one of these, you can just add Abreva, and it's acyclovir topically. And again, it will mutate the viral DNA more than it'll hurt ours. So there you go. The last one, sometimes when your patient has hepatitis due to hepatitis, usually B or C, we really don't have a lot to give them. There is a new class of drugs that are extraordinarily expensive, and if you have $1,000 per pill, and you're going to have to take them for 6 months, you can get treated for hepatitis C, but few people can afford that. So the only option is the old option, and that's interferon. Interferon, quote unquote, interferes with viral replication. So, what does interferon do? It interferes with viral replication inside the host cell. Typically, interferon is prescribed to patients with the hepatitis viral disease. Interferon is a chemical that is normally made by cells. Interferon is an emergency chemical signal, kind of like a hormone, but it's made by many cells, like white blood cells. They're made by your cells when there is a viral infection. Now, the cell that makes the signal is a goner, but it can send it out to the other cells. Now, sometimes patients will get a viral infection, but they're not making enough interferon, so the drug is prescribed. What does it do? It shuts down cell manufacturing processes. So if the cell isn't manufacturing anything, then the virus can't be manufactured either, right? But it's very toxic. Took years. We've been tweaking it forever. There are many types of interferon. Many patients will tell you that they wouldn't have even gone through therapy except for the love of their family and friends, loved ones in general, because it's horrible. I guess they say the only way you can think of this is if you had the worst case of influenza nonstop for months. That's what it's like to take interferon. But the option is probably death, right? So there is another method though. They're called interferon inducers, and they make the body think that they actually trick the body into making more of its own interferon. It makes the body think, oh, recognize that there's viruses around, is what it does. I won't go into the details, but that's what it does. Let's do some questions. Which of the following drugs is a DNA analog for guanine, guanosine actually, and is used to treat herpes viruses? AZT, acyclovir, penicillin, Tamiflu, or interferon? Acyclovir is correct. Okay. So, which of the following drugs is prescribed to treat influenza, but is essentially worthless unless treatment begins within 24 hours of the onset of symptoms? AZT, acyclovir, penicillin, Tamiflu, or interferon? Right, D, Tamiflu. It's not going to work. It's not. Okay. This very toxic chemical interferes with the replication of hepatitis viruses. AZT, acyclovir, penicillin, Tamiflu, interferon. Interferon. Interferon interferes with viral replication. So what would penicillin do to any of those viruses? Again, nothing. Penicillin, the antibiotics, only attack things that bacteria have, right? Only things that bacteria have. Viruses have a protein capsid, they have nucleic acid, and maybe some unique enzymes to attack. That's it. Okay, Precautions when you are taking antibiotics. We need these. We need to be good stewards and we need to teach other people. You need to teach other people. I'm only going to be your teacher for a few more weeks. So you need to go forth and be good stewards of antibiotics, okay? So, number one, vaccinate if possible. But Sally, we can't vaccinate for every infectious organism. So, and for reasons that I'll cover next week, okay? But if you can vaccinate, don't use antibiotics unless absolutely necessary. Be good stewards, okay? Do we really need to put all these antibiotics into feed? Okay, they stopped it in Europe. Now, mind you, again, it's not the farmer's fault. They're trying to make a living and they barely make a profit. But we just need to rethink the way we do things. Myself, now, when the time comes, maybe you can afford to get antibiotic-free meat, okay? But right now, I know you're paying debts. Use the correct dosage to overcome the infection quickly. Do you remember some antibiotics do not kill? Remember, they're the protein synthesis inhibitors like Z-Pak that will go in and they will stop ribosomes. They block them. The bacterial cell isn't dead. So, what if you didn't take enough antibiotic to block every single ribosome in every single bacterial cell? Well, they'll have other ribosomes to make proteins. And they're not dead. So, they can always make more ribosomes. So, and they'll be fine. You won't be fine. They'll be fine. Never take someone else's prescription. Remember chlorphenicol. Take the complete prescribed amount, even if you feel better. Symptoms are almost always the product of the inflammatory response. It's your immune response. When you feel better, it's probably because you aren't responding as violently to the invasion. Just because you don't have a fever or aches or anything like that doesn't mean the bacteria still aren't hiding in the crevices of alveoli, hiding in biofilm, all over your body. So please take the complete prescribed amount. Also, look at point number 3. Change the antibiotics at the first sign of resistance. So when do we know it's not working? And again, the antibiotics may not be working for many reasons. Maybe the drug is narrow spectrum and it knocks out gram positives, but you have a gram negative. All right. Or maybe the bacteria in your body have developed a mutant gene and they're resistant. Okay. So what normally would have worked on them doesn't. So you had Staph aureus, and regular Staph aureus penicillin would have been fine, but one of your Staph aureus bacterial cells developed a mutation. Now penicillin doesn't work. Okay. Give your patient 3 days, 3 full days. Okay. If the symptoms are not decreasing in severity, okay, then get on the horn and call the doctor, the nurse practitioner, the physician assistant, okay? Tell them, and they'll change antibiotics, okay? Use combinations. There are a lot of, and I'm going to use the B word, there's a lot of bugs that are multi-drug bugs. So, for example, Pseudomonas aeruginosa is an combination antibiotic bug. Tuberculosis definitely is. Pseudomonas, maybe not, unless your patient has, you know, uh, oh, certain conditions and you suspect resistance. But um, tuberculosis is always a combination. 3 drugs to start with, and then down to 2 because the third one's so toxic. Okay. All right. So antibiotic resistance. So if a patient is told that they have antibiotic resistance or something's going on and they hear the word antibiotic resistance, how do you explain this to a patient? Well, When you take antibiotics and you are not good, taking them correctly, then you develop resistance. No, no, wrong. Nope, nope, that's not how antibiotic resistance is occurring. It's not about you at all. The bacteria develop resistance. Bacteria have resistance. They always have, and they always will. And the antibiotics select for antibiotic resistant strains. That's what they do. So don't tell the patient. It's true when we abuse antibiotics, that selects for the when we abuse antibiotics, that selects for the antibiotic resistant strains. That's what it does. I know. Now, you can be resistant to sleep aids because sleep aids affect you. Okay. But but no, this is all about bacteria and bacterial cells. It's not about you. Antibiotic resistance, not about you. Hey, let's ask some questions. Hey, speaking of resistance, MRSA stands for metronidazole resistant Streptococcus pneumoniae. B. Methicillin-resistant Staphylococcus aureus. C. Metronidazole resting Staphylococcus aureus. D. Mitochondrion relay Saccharomyces aureus. E. Mitochondrion-resistant Streptococcus pneumoniae. Okay. Yes, B. You knew that. Methicillin-resistant Staph aureus. So what is this organism going to be resistant to? Probably more than methicillin. This should really be multiple resistant Staph aureus. So then what do we give the patient? Vancomycin. If not that, there are some others, hopefully, if it's not too late. If you treat a eukaryotic protozoan like Giardia or Trichomonas, which of the following would be the best agent? Remember, they have flagella. So, metronidazole or flagyl, vancomycin, tetracycline, penicillin, erythromycin. Yes, of course. Metro. Flagyl is what we use for Giardia or Trick. Okay? Yeah, it breaks up the DNA. All right. Which antimicrobial causes photosensitivity, tooth discoloration? Could be found in Kentucky Fried Chicken or any other chicken raised in the U.S. and should not be given to pregnant women or developing children. Penicillin, tetracycline, chloramphenicol, erythromycin, or ciprofloxacin. B, tetracycline is correct. Good. Which of the following inhibits DNA synthesis and can be pretty toxic? Cephalexin, chloramphenicol, tetracycline, erythromycin, ciprofloxacin. Cipro, right? Yeah. Okay, Cipro. This class or type of drugs has the best selective toxicity. Fluoroquinolones, chloramphenicol, beta-lactams, macrolides, polymyxin B. Of course, are nice little beta-lactam drugs. Yep. Fluoroquinolones, toxic. Chloramphenicol, yeah, remember, destroys bone marrow in 1 in 20,000. And polymyxin is a membrane permeability inhibitor. A 60-year-old female presents with a standard Staph aureus gram-positive respiratory infection. Which would be the best antimicrobial? Penicillin, anything broad spectrum, chloramphenicol, gentamicin, bacitracin. What are you going to give her? Penicillin, absolutely, pound for pound. If it's just regular staph, not resistant, and she doesn't have any allergies, it is the best. Broad spectrum would wipe out her normal microbiota and she'd end up with a yeast infection. Chloramphenicol, she might end up with missing the ability to make blood cells. Gentamicin, she might end up with hearing loss or without kidneys and be on dialysis. And bacitracin, that's never given orally. So this drug is ototoxic, can cause deafness and nephrotoxicity. Basically, it can put you on dialysis. Which one was that? Carbapenem, K-Flex, ampicillin, gentamicin, erythromycin. Well, the first three are nice little beta-lactam drugs, not them. Gentamicin. Erythromycin is another protein synthesis inhibitor, but it's not as nasty as gentamicin. But again, if you need gentamicin, you take gentamicin. Hopefully you don't have to take it till later on in life. Ah. Another shout out to infection control nurses. Again, you guys, some of you might be this person. You need to go out and tell patients, well, you have to tell you need to tell staff and, other nurses especially, you know, wash your hands, use universal precautions, you know, protect your patients. Okay? Little Darwin. Remember, the bacteria are always going to mutate faster than we can get new antibiotics. But because they can mutate very quickly, it's not because they're strong, it's not because they're intelligent, they're not thinking this out. They just mutate very, very quickly, and they are the most responsive to change. And that's what makes them the strongest. Have a good one.